Yeah, good morning, everybody. Today we will learn how to find the limit of any function, and we will start by function that is approaching a specific point, like the limit of f of x if x go to a point L. The limit helps us understand the behavior of a function near a specific value, and there are several methods that we will go over to find this limits. So the first one is direct substitution method. First, the simplest method is the direct substitution, and this works when the function is continuous at a specific point we are interested in. So, for example, we want to find the limit of f of x go to 2 of this function, limit of 3x plus 1 when x go to 2. You just substitute 2 there and you get directly the limit. So that means the limit is plus 7. However, sometimes direct substitution doesn't work, and it gives us, especially if it gives us some weird values such as 0 over 0 or infinity over infinity. In such case, we can use factoring method. So factoring method will help us. So let's say we want to find the limit of this function when x approaches 2. So if we substitute 2 here, we will get 0 down and we will get 0 up, which is indeterminate form. So in this case, we try to factorize to see if we can factorize. And fair enough, we can see that this is x squared minus 2 squared over x minus 2, which is x minus 2 times x plus 2 over x minus 2, and we can just simplify by removing x minus 2 because we have it at the top and the down, and from there we can calculate the limit as the limit of just x plus 2, and then you can use the substitution of 2, which give us the limit as 4. Another method is rationalizing, which we use when the function has square roots or another irrational expression. For example, if we have this function, limit of this function when x go to 4, same thing, if you substitute 4 here, it will give you 0 down and same thing 0 up. But we see that we have the square root here, so try to use the rationalizing, and we can multiply by the conjugate to eliminate the square root. So I will multiply by the conjugate of this one, so we can get rid of the square root. So we will multiply by square root of x plus 2 over, and we will divide by the same thing, square root of x plus 2. And then we can simplify our expression to get it as this. So because you will have square root of x times square root of x, which will give you x, plus 2 square root of x minus 2 square root of x minus 4, divided by this x minus 4 times square root of x plus 2. This will go by itself, and we will get x minus 4 at the top and x minus 4 on the down, and we will remove it. Then we can get our simplification form. They simplify the expression, and then we can use the substitution method. There is another method which called the Hopital rule, but we will do this and a specific class, just because it is very, very important, and there is some derivation involved there. So we will talk about derivation, and then we will show you how to use the L'Hopital's rules. There is another method which is specific trigonometric limitation or limits. Look at this limit. Limit of sine x over x when x go to 0. You know that sine of x, sine of f0, sine of 0, so this is 0. So sine of 0 is 0. And then you will get 0 over 0. It does not make sense. However, you can just memorize that the limit of sine x over x is 1, and you will use it. But when you get in high level mathematics, you will know how to develop this. But for now, just to save some time in your when you are solving your problems, just memorize that this limit of sine x over x when x go to 0 is 1. Same thing for limit of 1 minus cos x, because cos 0 is 1. So we will get 1 minus 1 over 0, which will be 0, 0 over 0. However, if you memorize this just as the limit of 1 minus cos x over x when x go to 0 is 0, will save you a lot of time. The other method is the squeeze theorem or the sandwich theorem. This is also a very, very interesting method, because sometimes a function may be too complex to handle directly, but we can squeeze it or use it as a sandwich between two simple functions, and get your function, like your function f of x, squeeze it between two other functions that you can easily find their limits. So if you see that it's hard to find the limit of this one, you just get it squeezed between two different functions, and the limit should be one of this. So for example, the limit of x squared sine 1 over x, if x go to 0, we can squeeze we know that sinus of anything, it's always between minus 1 and 1. So then if we multiply by another x squared, so you get minus x squared and x squared. So we know that this function is squeezed between minus x squared and x squared. So you just find the limit of this function of this function, and it will be same as this one. Fair enough. The limit of x squared or minus squared when x go to 0 is 0. Then the limit of this complicated function is 0. Okay, now let's talk about the limit at infinity, not at a constant as we saw before. So if you have the limit of f of x when x go to plus or minus infinity. Let's start with the rational function, because polynomial function, just this one need a whole lesson by itself. So let's talk about the rational function. Which are functions that can be written as the ratio of two polynomial functions. Like we can find your function as something above something. To find the limit of rational functions as x approach infinity, plus or minus infinity, we compare the degree of the polynomials in the numerator and denominator. What we mean by this? So we have three cases. The first case is if the degree of the numerator is less than the degree of the denominator. So for example, if you have a rational function that have the upper side is less than the downside, for example, we have this function, the limit of 2x plus 3 over x squared plus 1 when x go to infinity, Here the degree of the numerator 1 is less than the degree of the denominator, which is 2. As x becomes very large, the denominators grow much faster than the numerator. So in this case, the limit goes to 0. Okay, please remember this. When the degree, the numerator is less than the degree of the denominator, we can see that the denominator, the downside, grows much faster than the numerator. So because this is growing faster than this, so you can directly say that the limit is 0. And fair enough, because the limits of anything above the infinity, so it will be 0, because this one grows faster than this one. The second case is the degree of the numerator is equal to the degree of the denominator. For example, 3x squared plus 4 divided by 2x squared plus 5. Here both the numerator and the denominator have the same degree. So the leading coefficient of the numerator and denominator dominate the behavior of the function as x grows larger. So in this case, you just keep these two and you simplify the x, for example, the x squared, and you will get left with 3 over 2. Okay, I will repeat this again. If you have the numerator and the numerator have the same degree, for example, 3x to the power of 5 over 5x to the power of 5 plus something and minus something, we don't care about all this thing. We only care about this, the leading factors with the same degree. In this case, you cancel the x with its power, and whatever you left with it is the limits. The third case is the degree of the numerator is greater than the degree of the denominator. For instance, if you have x to the power of 3 plus 2x plus 1 over 4x to the power of 2 plus 5, in this case, the numerator has a higher degree, which is 3, than the degree of the denominator, which is 2. As x increase, the numerators grow much faster. So this section grow much faster than this section. In this case, this will cause the whole function to increase without bounding. So if the limit of this function goes to infinity plus infinity or minus infinity, same thing will do for the limit. So the limit of this function, if x go to plus infinity, will be plus infinity. If this increase to minus infinity, will be, but keep in mind this degree. If this is like 3 or 5 or whatever, it will be minus infinity. But if it's square and we have 1 here, it will be plus infinity. So to recap this, if the degree of the numerator is greater than the degree of the denominator, in this case, the numerator grows much faster than the denominator, causing the whole function to increase without bounding. Okay, next we will let's consider the exponential function, where the variable x is in the exponent. So there is like two cases in this case. The exponential growth, for example, the limit of exponential of x when x go to infinity. The exponential function like e to the power of x grow extremely faster as x increase. As a result, the exponential function e to the power of x approaches infinity as x approach infinity. So for instance, the limit of exponential of x when x go to infinity is infinity. Okay, the exponential decay is when you have the exponential function like this, e to the power of minus x, where the exponent is negative. The function approaches 0 as x increase. So when this x increase, the whole thing approach 0, because the negative exponent cause the value to shrink, which will make it going down towards 0. So the limit of exponential of minus x when x go to infinity will be 0. So let's see one real life example. For example, we have this function x squared times e to the exponential of minus x. So we need to find the limit of this function as x grows to infinity. Okay, so we can see here that we have two exponent function. We have x squared and we have exponential of minus x. If we do substitution, we have infinity here and we have infinity here. So this one goes to infinity, but this one goes to actually down. This one is like shrinking the function. So which one is dominating? Based on what we just said, this will be the dominating one. So immediately you can see that this shrink the function faster than this one. So you can directly say that the limit is equal to 0. Another example, we can have the limit, we want to know the limit of this function, exponential of x plus x squared divided by exponential of x. We need to find the limit when x go to infinity of this function. So this is a ratio of two functions where the denominator, this one, where the denominator e to the power of x plus x squared, and the denominator e to the power of x. To simplify, divide each term in the denominator. So we will get this one divided by this plus this one divided by this, and we will get 1 plus, we will get his limit same as the limit of 1 plus x squared to the e to the power of x. And this is like as x approaches infinity, this term approaches 0, because the downside shrink the function very quickly than the x squared, though the limit will be 1 plus 0, which will be 1. Okay, same thing if we take another more challenging example. I like to have more example in this case, because it will actually show you how actually thing works. So for example, if we have this function e to the power of x minus x to the power of 3 minus x to the power of 3 divided by e to the power of x plus x to the power of 3. Here the function is a ratio where both the numerator and the denominator involve a combination of exponential and polynomial term. We need to factor out this out, so we can have this out. So this will give us e to the power of x times 1 minus x to the power of 3 divided e to the power of x divided by x to the power of x 1 plus x to the power of 3 divided by x e to the power of x. Now we can just simplify by this, so removing this, so we will get just the other parts. So as x approaches infinity, this term actually approaches 0, because the downside caused the function to shrink very fast. So the whole thing goes to 0, the whole thing go to 0, so we will lift up just with 1. So now for the limit involving logarithm functions. Logarithm functions where the logarithm is applied to the variable x increase very slowly compared to polynomials and the exponentials functions. For example, the limit of log of x, if x go to infinity, although log x grow without bounds as x increase, it does so very slowly compared to other function, polynomials and exponential ones. So the limit of this function will be infinity. So let's see some examples involving logarithms. Log of x divided by x squared. So the function has a logarithm in the numerator and a polynomial function in the denominator. Since the logarithm growth is much slower than, so this grows slower than this. So the polynomial function x squared will be dominant, so the limit when x go to infinity will be 0. So like you have something over infinity which give us 0. So you just ignore the log because it grows slower than the exponential function. Another example is the limit of log of x divided by x. In this function we have a logarithm function which is log x in the numerator and a linear function which is x in the denominator. As x approach infinity, the log of x increases but much more slower than this. So this also increase lower than this. So the denominator x grows faster, causing the entire function to also to approach 0 when x go to infinity. So because this is dominant above this, so you just have as you have the limit something above infinity which will give you 0. So how about if we have a combination of logarithm and exponential? So for example, we have this function log of x over the exponential of x. In this function, the log of x is in the denominator and exponential x is in the denominator. While log x increase as x increase, however, the exponential function e to the x grow much faster, causing the function to shrink and goes towards 0. Same thing, you will have something above infinity if x goes to infinity, which will give you 0. Okay, now to solve limit involving piecewise function, which is another type of limits, you need to consider the behavior of a function on either side of the point where the limit is being involved. So there is some steps by steps to do that, but we will do them as examples so you can actually grasp this better. Always the piecewise function have a form which is like something here and something here, if x is equal to this and if x is equal to this. For example, let us see one example. For example, if we have f of x is equal to 2x plus 1 if x is less than 3, and x square minus 5 if x is greater or equal than 3. So here we have a piecewise function which is have two parts, which is when x is less than 3 or when x is equal or greater than 3. So to find the limit of fx as x approach the approach 3, follow these steps. So we need to find the limit at left side of the function when x approach 3, which is to find the limit of f of x when x goes to 3 from the left side, which is negative 3, or we can write it as x to the power of a small negative of fx is equal to the, because we have our function is like this, is equal to 3 to x plus 1 if x is less than 3, and x square minus 5 when x is greater than or equal than 3. So in this case we have x is equal to 3, we have 3. This is the left side, so this is when x is negative, and this is the right side. So for the left side we will take this part, for the positive side we will take this side. So we will apply our function in this case as follow. So it is equal to the limit of 2x plus 1 when x go to 3, which gives us, you just substitute 3 there, 2 times 3 plus 1, which is 7. However, if you are looking for the limit of fx when x goes to 3 from the right side is equal, you take the right side function, which is this. So it is equal to limit of x square minus 5 when x goes to 3. Same thing, you just substitute there and you will get your limits. The left hand limit as x approach 3 is 7, and the right hand limit as x approach 3 is 4. And from here we can see, as two limits are different, are not equal, we can say that the limit does not exist. And the opposite, if you have these two limits are equal, we can say that the limit exists, and it is that number which we find. What we did right now here in this example, we actually did the continuity check, because we find if there is a limit, and we find there is, yes, there is a limit at left side and there is a limit at right side. So there is a limit, so we check there is a limit at x approach that point, which is 3, and from there we compare the both limits, and if we find the both limits are equal, we can see that the function is continuous at that point. But if we find the limit is different, we can say that the limit does not exist, which means the function is not continuous. Since the left hand side 7 does not equal the right side limits 4, the overall limit as x approach 3 does not exist. And since the limit does not exist, it cannot equal the function's value of x is equal to 3. So to recap for this one, for the check, the continuity check, the function of fx is not continuous at x is equal to 3, because the limit as x approach 3 does not exist. For a function to be continuous at a point, the limit must exist and be equal to the function's value at that point. Last method that you can find the limit of a function, and it is always also sometimes very, very useful if the function is very, very complicated and you cannot actually grasp or see how it's behaving. You can draw that function and see how it's actually behaving at specific points. For example, I will give you one example that I saw just yesterday. We saw this function like is behaving like this. So the function was like this, and the question was to find the limit as x goes to minus infinity. So when we graph, the function is very complicated to do it algebraically, but when we graph this function, we can see that as x goes to minus infinity, we can see that function goes to plus infinity, just from the graph, because the function was very difficult to handle. So to recap, functions, graphing a function can also be helpful to find the limit of a function when it goes to infinity.